Okay, first to Deepak. Congratulations, Deepak. And so Deepak and Mustansi both have been very helpful to me throughout my career. So I also thank you for my personal note, though I'm not involved with TIFR. But my interaction with Deepak, and so I was working on imagery turbulence. This is my story or joke on I was working on imagery turbulence many years back. So I tried to tell him about this. So Deepak's response to this field was this. So I don't know whether you can read Hindi. Karela ninja. So this is the fruit. Some people who are international, this is a fruit which is very bitter. And so that's what he said about this. So I knew that he is not so keen on this topic. But in any case, I really liked the discussion with him. Okay, so let me get to what I'm trying to get to is emergence of order in 2D Euler turbulence. And it is an isolated system, but it gets ordered. Now, ordered we see visually, but we try to quantify it using a measure. So this comes in a project which also kind of tells us that this is looks like a contradiction, no? Turbulence in equilibrium. But there are this equation, like Rahul gave a nice introduction, that there are equilibrium solutions of both Euler and Navier-Stokes solution equation. So this is a STATISTICAL project which we are working on. So these are my books. So in fact, I like to write. So this is where I take some of the material from this book. So these are the papers. This came recently. So that's for reference. Okay, so Euler equation, Rahul gave a nice introduction, but I just want to tell that I have incompressible Euler. Abhishek has worked quite extensively on compressible Euler where he drops this condition. So this equation has no viscosity, right? No viscosity and no external force. So it's an isolated system. There's no energy coming into it and there's no dissipation. So no forcing, no dissipation. So there is no heat coming into the system or going out. Basically no heat going out. So thermodynamic entropy is constant. Change in entropy is zero. So thermodynamic entropy is constant. It's well known. I mean, Landau's book has a very nice introduction to this equation. So, but we'll find that it does, like in fact Rahul's talk, you see that things do get changed, order changes with time. Okay, so I will try to quantify that order. So just to recap, I mean, some of you are probably not too familiar with this. So I will recap some of the things which Rahul did. So equilibrium solution of Euler equation. It has equilibrium solution, which was told by T.D. Lee and Kriegman. They did it many years back, and which Rahul did show before, but I'm just trying to give you a quick picture of what the solution is look like. So in equilibrium, okay, that means detailed balance will be respected. The solution is one solution, okay. There are certain conservation laws like kinetic helicity that complicates this equation a bit more, but without kinetic helicity, it's just white noise, just like thermodynamic gas. It's as white noise as thermodynamic gas. So Fourier transform of this will give us constant modal energy. For each Fourier mode, energy is constant. So in 3D, because the number of modes in a shell is k squared, the 3D energy is k squared and 2D is k. So I will focus on this one. So equilibrium solution, we'll see, we'll try to get whether it is possible or not. I mean, Rahul did show for 3D and 2D also. We can get it equilibrium solution quite easily in the next. Yeah.
Is that Kmax because it's truncated Euler or it's
yes, truncated Euler. I am working with truncated Euler. So with kinetic helicity, just to tell you that there's a u dot omega is a constant, so that makes it complicated, as I said, this term. And in 2D, because the entropy conservation, this term is coming extra. Okay, so Ansagar's paper, which is, I think Rahul told the paper 2. The paper 1 itself is very nice. And this is looking at Euler equation in 2D. And negative temperature, I think probably first time it was introduced in this paper. Here is a I think Deepak's talk is connected to this. It's a constrained system. This volume is constrained, and Ansagar maps Euler to Hamiltonian system, and then he gets here. So this is a nice picture coming from this paper. So at small temperatures, or basically small energy, there's no temperature. Huh? This is a conservative system, disconnected heat bath. At small energy, there's a anti-vortex-vortex pairing. At infinite temperature, it is all thermalized. But go above infinite temperature, which is negative temperature, we get clumping of vortex and anti-vortex separately. Very similar to what Hughes gave a talk. This is very similar to that. So this does tell you that this white noise is not the only solution. In 2D, there are possibilities of these large structures to appear in the solution. So now we'll just do a numerical solution to check whether we get some of these solutions. So we use this code, spectral code, and this scheme is very nice scheme, which gives a very good accurate energy conservation. We need to conserve energy, and code should not blow up, and it comes there. 3D, Rahul, so okay, let me tell you. So one thing was to start with organized structures and get to the equilibrium state, which Rahul showed, Rash's group. But we can start with random white noise, and we are there already in the solution. We start with random white noise, and this is the one snapshot of a 3D cut. We take a horizontal cut, and there's white noise, we get Maxwellian. Spectrum is flat when we divide by k squared. So energy is like k squared. And this is, I want to spend a bit of time. So in turbulence, traditionally, we talk about energy going out of a wave number sphere. Okay, this Kolmogorov flux, energy coming out from large scale to small scales. So this is a wave number sphere. So every sphere has energy coming out in 3D in Kolmogorov picture. Okay, so we can compute it using some formulas. So in Kolmogorov theory, there's a viscosity, right? Please keep in mind, and there's a source in a sink, and there's energy going down in this path. But in Euler, there's no, well, ideally there is no sink. So there is a problem, okay? So that's what we get some differences with the Euler equation and Euler and Navier-Stokes. But in the equilibrium solution, they detail balance, and we get this k square. So quickly, this is Rahul showed that. So this organized structure, and it gets here at long time, and we get non-zero flux. The flux is non-zero. So we can check if it is non-equilibrium. This part is non-equilibrium. Oops. Another way around. Okay, anyway, this Rahul has showed already. So this is thermalizing. Okay? I mean, this is straightforward. And this is what is there. I just want to make few comments. This seems like to me is connected with David Hughes' talk. So I think there is a quantum, we can make this as a general picture. So here we have non-equilibrium part in the system, and the equilibrium part, just k squared. And so I just would like to say that friction, we can say this part is basically acting like a friction or dissipation. And it's just getting sunk there, even though there's no viscosity. So this part basically acts like an effective viscosity out here. Now let's look at the 2D. 2D has some surprises. Okay, so 2D, if I start with white noise, okay, initial condition, then I get to, I'm already in my equilibrium state, and I get the normalized flux, which is this one, Ek into K, is flat. So energy is going as K, and my flux is 0. Okay, so this is straightforward. I mean, this is no surprise, but we get Krecknen or TDL solution very easily. But the question is 2D, I mean, can there be non-equilibrium final solution, asymptotic solution? Can it be non-equilibrium? There has been a lot of people, reasonable number of people, who are taking one side or the other. So for example, this paper does argue that 2D Euler asymptotic state is not in equilibrium. Okay, so that's what we wanted to see. In fact, if you look at it, the formation of hurricanes are essentially 2D Navier-Stokes solution. Now, these big structures are being formed and this inverse cascade. So you may expect maybe 2D Euler also probably may give those structures. And Onsager is telling us there are structures of that sort, but Onsager says it's equilibrium solution. But we should really check the detailed balance and whether they are the equilibrium solution or not. That's what we wanted to check. So these are the three initial conditions. This was done by my student, Somdeep Chatterjee. So these are three initial states. Run A, we start from here. These are basically 100 vortex, well, 50 vortex pairs. And start from here, we get here, and this gets logged into it. There are some small evolution around it, but it's basically getting logged into one vortex and one anti-vortex. Okay, we start with this initial condition, we get into a shear layer. It's not a vortex anymore, but shear layer. This one leads to two pairs of vortex and anti-vortex. So we are getting three different asymptotic states. Okay, for 3 runs. I mean, if you do more runs, possibly you'll get more. So these are attractors which are not in the equilibrium state. It appears to. I mean, at least not the TDL or Kreckner equilibrium state. Now, maybe it is new equilibrium state, possibly, where detailed balance may be working. So we wanted to check the flux and compare with the Kreckner stuff. Okay. So we look at the energy. Okay, these are verification that our state is function of time. It is not, it doesn't change much. So please keep in mind that, well, it is long enough time that it is a steady state, but okay. So we look at the energy spectrum. This part, so there are 3 runs, the 3 plots. For large wave numbers, these dashed lines match with Kreckner prediction. So Kreckner gave a formula, if you recall, beta plus gamma k squared at the bottom. So that leads to 1 by k at large k, and these are the 1 by k solution at large k. So entropy is playing a pretty important role, but at small wave numbers, it doesn't fit. Small wave numbers, those formulas don't fit. So looks like there's something odd, something wrong. We look at the energy flux, which I described, the energy coming out of the sphere. We find that there's significant negative flux, but they keep fluctuating. We didn't show the fluctuations here, but they fluctuate, but they are very significant at small wave numbers. Again, telling us that these vortices are doing something interesting. And this is non-equilibrium. Okay, so I'll show you, I'll prove one more way that this change in energy d by dt is Tk. So this is another way to verify equilibrium or non-equilibrium. So this is energy of a shell, okay, we wave number shell, or you can think of a mode as well. So the Tk, if is 0, then energy will not, basically that equilibrium state will require that Tk is 0. So most Hamiltonian systems, supposedly, I'm not expert of this, but this is what we should get, and we get it for Burgers and this under equilibrium state. But for 2D, for wave number shell 1, 2, 3, there are significant oscillations around 10 power minus 2. So these are telling us that they are not in equilibrium, they are fluctuating. Now, so this is 2D Euler. I hope I can convince you. I have convinced you that it's out of equilibrium, and I think they are connected with possibly other systems, which are, some of them are out of equilibrium, especially in quantum systems. Now, so how to quantify the order? Thermodynamic entropy is constant, right? By definition here, no heat generation. So then we thought about a new measure called hydrodynamic entropy. So we defined Pk, probability for wave number k, as Ek by E. Okay, so this is energy. So this is a multi-scale measure. So this is Pk. Then Shannon entropy formula we import. So minus Pk log Pk. And this is what we'll try to give it for different frames. So this is for a given frame at a given time, I can compute it. It's not over ensemble. This is a, like basically following Shannon. So in 3D, entropy for, this is the work by Brachet's group. So entropy does increase and it flattens to the maximum possible entropy. Okay, so it is thermalized. It's a clear signature. But in 2D, we find that Basically, we start from here, but the initial condition can be anywhere. But there is a region where entropy decreases. Okay? Hydrodynamic entropy, okay, not thermodynamic entropy, is decreasing for all the three cases, is decreasing here. Okay, so system is getting more ordered with time. But it is not a violation of second law because thermodynamics is not getting affected here. Okay, but things do get ordered with this, even though it's an isolated system. Okay, so I just want to take 1 minute on arrow of time. This will be so here. So thermodynamic entropy seems to be thermodynamics is not very useful for hydro. Okay, let me say this. This Kolmogorov cascade. In fact, for Euler, entropy is not playing any role in the strict sense, the thermodynamic entropy. So then how do we define arrow of time? If I think that growth of entropy is the arrow of time, then I said, well, let's use energy flux idea. So this one question, which movie is it? Is played backward. Okay, this is of course played backward. So we can figure out it's played backward. But in a hydrodynamic flow, can we figure out if the movie is played backward? Okay, the question is, if a movie which is played forward, I see the movie or somebody plays it backward, can we identify it? So very easy, you look at energy flux. In the forward movie, the energy flux will be positive. We can measure it. Well, I didn't tell you how to measure it. Energy flux will be going from large scale to small scale by Kolmogorov formula. Okay, but in the reverse movie, energy will go other way around for 3D. It will go from small scale to large scale. So I look at the picture. I don't even need to look at the structures. I can just use mathematics to see the flux. If the flux is negative, then I know it's a fake movie. The way this is also a fake movie. Okay, so this is a nice way to see it. That asymmetric energy transfer in driven non-equilibrium system can define error of time, including in Euler equation, which is non-dissipative. It works well for Navier-Stokes, but we can talk about it for Euler as well. So this is what I will end here with the conclusion. Thermodynamic entropy, well, for isolated system, it can get more ordered. Okay. Now, I think there are popular talks, no, say, well, everything is disordered, including the books on my desk. I mean, I think there's of course popular talk, but things can get more ordered. This is one example. Okay, and a quantum connection, which I'm interested in, but I'm not good at it. So a self-gradating system, isolated, possibly you can apply some of these ideas and arrow of time using energy transfer. I hope, yeah, this could be something interesting. Thank you.
Okay.
Yeah. What did it say? Which movie? Deepak, you know? You know? Which one? No. Diwar. Right.
Like the way you define for Liouville.
Yeah.
Right? And then can you show that entropy increases with time, or if I just take a part of the system and
I
just
know, but phase space for this is huge. It's 512 squared.
but if I can take a part of the system and restricted phase space.
Okay. So phase space is, of course, the velocity mode. So all of them make a phase space. Of course, a projection may be, I don't know, we have not tried it, but it's a good idea, I think.
So the system is not Hamiltonian, right?
2D, well, it was mapped, it has been mapped to Hamiltonian. Like
so if I take the then full phase space, then the entropy will not change, I guess, right?
Yes. Entropy, the area is conserved. If I take
like the H theorem or
yes, that is
if I take a part of it.
That's right. The phase space volume when it evolves, but it's a big phase space, it doesn't change with time. Yes, for Euler.
If I take a part of it,
no, it can change. It can change. Yeah, no, part can change. I didn't think of that. No, possible. I think.
Yeah, exactly.
I see. Okay. I see. Yeah, I need to look at it.
Okay, yeah. So I had one question.
Yeah.
I mean, so if you look at the Euler equation, I would imagine that the entropy is generated only after you have the shocks, right? I mean, it should be at the shocks.
No,
isn't it?
here there's no shock because of incompressibility.
But you're saying still there's entropy production.
There's no production, it's just getting more ordered. Because of inverse
but there's no
cascade.
entropy, but like it doesn't increase with time, right? If you just do Euler without
Entropy 2D decreases with time. In 3D it increases with time. 3D increases with time. But it's
no, but with shocks, right? Without shocks, there's no entropy change.
I think thermodynamic entropy is constant.
Right, yeah.
Thermodynamic entropy requires heat generation.
Yeah.
But this is different entropy.
Oh, this is not thermodynamic.
This is not thermodynamic entropy.
Okay.
Thermodynamic entropy is constant for us.
Okay.
Yeah. Yes. Yeah.
Sir, if we see the structure function of this order to disorder and disorder to order, then whether we can say anything about that, like it will different or same structure function of
the turbulence structure function?
Yeah.
No, it should be connected with energy spectrum. So the way energy spectrum got locked into, remember the 2D way I showed you is somewhere. So structure function is like what will give same information as energy spectrum. Okay, so so it is going to be steady, approximately. If you average it out, we have a lot of frames, and it should give us some kind of inverse cascade. Well, it fluctuates a bit, but that negative energy flux kind of should be, yeah, this picture. This should be coming from structure function as well. We didn't look at it, but yes. Yeah, so for example, this point is plus and this point is negative. Overall, well, the idea is the following. So we have a lot of, let's say 4 players and ball is being passed around. So equilibrium will say, well, no ball passing, everybody is sitting quietly. But here ball is, this energy is being flowed around among themselves. So there's significant energy exchange is happening among low wave number modes. But nobody keeps the ball for a long time. So I get it, I pass it to somebody else. I don't pass it to the same person. This juggling around, and that is clearer here in this picture. Oops. This is a better picture of energy. So no Fourier, you can see it is oscillating, but the energy was gained for k equal to 3, but then it lost it here. So it is basically exchanging among themselves.
Okay, so last question, Deepak.
So these pictures remind of some very old pictures of Fermi, Pasta and Ulam, where they showed that if you take some couple nonlinear oscillators, the energy in one particular mode keeps on varying like this,
right.
Which was just a sign of integrability, let us say.
Okay, the 2D Euler I think is not integrable.
Okay, it's okay, but it has some modes in which the energy keeps changing.
Yeah, it keeps changing. Okay. I agree with that. That is what is happening here, and that is what is making it dynamic, indeed.
But in FPU, it seems like if you wait for long enough, it people have run now like even longer than it seems it equilibrates. So I don't know. This also might be a transient.
So,
of course, I'm like.
Okay, we ran to 170. We plan to run higher, a longer time, but. Well, it was locked, so you can look at the time series of the entropy itself. It is flattened here. It is flat for quite a while. Okay, this part is flat. This part is so t equal to 10 to 30 in basically scale times. Okay, so maybe, but it's unlikely. That's my bet. Okay, it's unlikely.
Okay, so let's move to the next topic.
Thank you.